Hello, everyone. My name is Dr. Zahur Ullah. I'm a lecturer in the School of Mechanical and Aerospace Engineering at Queen's University, Belfast. So Queen's University is the ninth oldest university in the UK. It is a member of the Russell Group of top research intensive universities in the UK, and it is ranked 8th in the UK for research intensity. So I'm working in the School of Mechanical and Aerospace Engineering, which is this white building in the middle, with a total of 104 staff, including 43 academic staff and about 30 postdoc research fellows. In the school, we have total of 870 students, including 800 BEng, MEng, and MSc students, and about 70 PhD students. So I'm working as part of the Advanced Composite Research Group. So the group consists of academics, postdoc research fellows, and PhD students. So just to give you a brief idea of my research interests, so I'm mainly working on developing new numerical techniques for problems, including solid mechanics problems. So as you can see, I developed a nonlinear adaptive meshless method. So meshless methods are the same as finite element methods, but instead of mesh, we are just using nodes, and therefore it is most appropriate for problems such as uh, large deformation, crack propagations, and fragmentation problems. So as part of my research, I developed a nonlinear adaptive meshless method, and with both material and geometrical nonlinearities, so including both plasticity and large deformations, large strains. And these are some of the novel contribution from my side, including domain of influence, which was based on the Voronoi diagram. I use efficient neighboring search with a KD tree. And we also need error estimation procedure for adaptive analysis. So I use the procedure from Chung and Belichko. And then I also developed this refinement strategy, as you can see in this figure. So in 2D, I developed everything in MATLAB from scratch. And in 3D, I use MATLAB as a programming language. So as you can see, this is a simple plate subjected to unidirectional tension. And we can solve this with this adaptive meshless method. And as you can see, we start our simulation with a very coarse mesh or discretization. And then during the simulation, based on this error estimation, we can refine the discretization and to improve the accuracy of the results. And similarly, we can solve other examples. For example, here we have a soil block with some rigid footing on top of it. And if you apply load on the footing, so you will see the shear bend which will be developing here. So this means that the soil block will fail along these shear bands. And again, this can be simulated our code. So the problem with meshless methods are these are computationally more expensive as compared to FEM. So then the idea is to use meshless methods only in a region which is difficult to model using FEM, while in the remaining part of the problem domain, we can use finite element, as you can see in these figures. So, but we need to properly couple both meshless and FEM, and therefore I develop a coupling strategy between meshless and finite element. Now, as you can see in this figure here, we developed a new coupling procedure, which is what we call is adaptive finite element meshless method coupling. So the idea is that, for example, if you want to solve this problem. Again, the same footing problem on the soil block. So you will start your simulation with only finite element mesh, and then during the simulation, based on this error estimation, so I'm using this Sienkiewicz and Zhu error estimation. So you will convert a region into only meshless. So this purple region is a meshless zone, and the blue one is finite element zone. And then we can do refinement in the meshless zone because it's more easier as compared to finite element. And then we can obtain the limit load for this specific case, and we can plot the load displacement curve. I also developed some algorithm for meshless methods and coupled finite element meshless methods based on high performance computing. So I developed these 4 algorithms: so linear elastic, nonlinear, nonlinear adaptive, and nonlinear adaptively coupled. So again, I use these different libraries for this specific task, and I developed the code from scratch in Fortran. Now, as you can see in this figure here, that we can solve this beam subjected to some sort of loading. We can solve this in parallel. So you can see this is the partition of the discretization. And in this figure, we can see that if we increase the number of processors, then the simulation time decreases. And the speed up is also increasing with increasing the number of processors. And based on this, then we can solve very complex problems with very large deformation and with large strains and plasticity. So as you can see in this figure, that we have plate subjected to some sort of loading, and this was the undeformed configuration, and this is the final deformed configuration. And we can see a necking here, which shows that it's a very large deformation problem. Recently, I'm working on the multi-scale modeling of fiber reinforced composites material. So I'm using a strategy which is what we call is multi-scale modeling. So the idea is that on the macro scale, we assume that the structure is homogeneous, and then we include heterogeneities on the micro scale. So in this case, this is the micro scale. So we have matrix fibers and the representative volume element. This is the idea of the multi-scale modeling, that on the macro scale at a specific point, if we know the strain, so we can take the strain and then we can define a problem on the micro scale. Then we can solve the problem, and then we calculate the stresses, and we calculate the stiffness metrics and homogeneous material properties. So, and the code, again, we developed a code for it. The code is what we call is a MOFEM. So MOFEM is again a finite element analysis library. And for the preprocessors, we are using a qubit. We can also use Gmesh and Salomomeka. And for the post processor, we are using ParaView. So all these are free to try. And again, the code that we have is having some sort of flexibilities which you cannot find in the commercial finite element softwares. So we are using PETC and MOB libraries. We are using the code which is high performance computing. And we are using these arbitrary order of approximation. So this means that the code is based on the hierarchic basis function. And I also work on the composites laminates, as you can see in this figure. So if we take this composite laminate and we apply load on it, so we can see that the stresses at the center of the laminate is very small. But when you approach the free edge here, so the stresses are getting very, very high. So this project that I was working on was a Duracom project, which is mainly concerned with the durability of FRP composites. And I work in collaboration with the University of Newcastle, Bath, Bristol University, and Warwick University. And it was an EPSRC funded project, and we also worked with these some industrial partners. So I also worked on the long-term durability of FRP composites, again, as part of this Duracom project. So if you subject these FRP composites to some sort of hygrothermal aging, so this means that if these structures are in real life applications and will expose to high temperatures, low temperatures, and also humidity. So this will obviously decrease the mechanical performance of the structures or degrade the mechanical performance of the structures. So as you can see, we did some sort of experiments. So we subject these FRP composites to different sort of environmental conditions. So in this case, we put these samples in hot water. So for example, at 40 degrees centigrade, 60 degrees centigrade, and 80 degrees centigrade, and also at 25 degrees centigrade. And then we measure the different mechanical properties, including shear modulus, different strengths, and then we found that these mechanical properties degrade over time. So for example, this plot here is the shear modulus with respect to time, and then we developed some model from it, some mathematical model, and then we implement the mathematical model in our finite element code. And finally, this is just a numerical example to show that how this whole process works. So for example, if you consider this problem here, and this edge is subjected to very high temperature, and 80 degrees centigrade, and again, you apply some load here. So this figure shows that the moisture concentration is changing inside the material. And again, the temperature is changing inside the material. And then based on the moisture concentration and temperature, we can calculate the degradation in the material. And if the structure is degrading, so obviously for a constant load, we will observe some sort of displacement because the stiffness of the structure is degrading over time. I also work on the nonlinear micro-meso mechanical response of FRP composites. So if you consider FRP composites, so on the micro level, we have this is the representative volume element. So we have matrix and fibers. So again, I include matrix plasticity, and I also include fiber matrix decohesion. And these figures show the validation of the plasticity model that we are using for the epoxy resin. So if we subject the epoxy resins to unidirectional testing, so unidirectional tensile load, compressive load, and shear load, and again, we can validate that our simulation results are very close to the experimental results. And finally, then we can simulate unidirectional FRP composites, as you can see in this figure and in this figure. And finally, the same idea can be used to simulate woven composites or textile composites. So as you can see in this figure here, that you can subject these composites to a variety of loading, and then the code that we developed can predict the limit load, and it will be very helpful for designing these structures. So I also worked on the thin wall structures using this prism solid shell element, which is we developed for this specific case. And these are some numerical examples. So if you subject these plate to a lifting load here, so you can see it's very high deformation problem. And again, if you consider this this structure, which is a hemispherical shell, and if you subject this to radial loading, so you will see that you will experience this very high deformation. And again, we can calculate the force displacement plots for this case, and we can find that our results are very close to the some sort of experimental results. I also worked on the life extension of the UK nuclear power plants. So as you can see in this figure here, that it is a graphite cylinder slice test. So these graphites are mainly used in the nuclear reactors. And again, we can see that the code that we developed here so can simulate the crack propagation in these nuclear graphite sort of bricks, which is mainly used for moderation in the nuclear reactors. And the project was in collaboration with EDF Energy and Royal Academy of Engineering. And these are some additional tests that we performed. So this is a torsional test. So if you subject this beam to some torsional loading, and again, this is a mixed mode 1 and 3 loading in 3-point bending test. And again, our results are very close to the experimental results here. So finally, this is again, I worked on the contact mechanics. So I developed this motor finite element contact formulation. And the code can be used for toying non-conforming meshes. As you can see in this figure, that there is a very fine mesh here, and then it's a very coarse mesh here. And these are some of the novel contribution that we did. And again, this is some initial testing of the code. So the code, as you can see in this case, that we can tie these two non-conforming meshes. And again, in this case here, so this is just linear elastic example. And we also try to simulate a contact between the two blocks with even different meshes. The meshes are not matching with each other. And again, in this case, we can see that we can simulate even very high deformation. So currently, I'm also working on the multi-scale modeling of 3D woven composites. So normally we're using laminated composites or unidirectional composites. But the main issue with the laminated composites is their mechanical properties are not very good in the thickness direction or in the Z direction. So as you can see in this figure, so the 3D woven composites, we have yarns. In this case, is oriented in all 3 directions. So the green yarns are in Y direction, the gray yarns are in the X direction, and we have this red yarns which are in the Z direction. These 3D woven composites will provide you with very good sort of mechanical properties in the thickness directions, including fracture toughness, including impact, very good impact properties, and very good strength, mechanical strength. And again, we did some sort of simulations here. We develop a code for it, and the code can calculate the mechanical properties in the different directions. If you know the mechanical properties for each matrix and fibers on the micro scale. So finally, we can even simulate all these different sort of yarn architecture. So for example, this is what we call is a 3D orthogonal 3D interlock, and this is through the thickness angle interlock. And this is 2.5D layer to layer angle interlock and 2.5D layer angle interlock. So thank you very much for listening to my presentation. So again, if you want to discuss a specific project in detail, feel free to contact me. My email address is given here. And again, you can also find further information on my website. So thank you very much.